Okay, so we've learned what a rate equation is, and we found out, for example, sometimes rate is equal to rate constant a to the power of 1, b to the power of 1. Another reaction, that's reactions between a and b, and other times it might be b to the power of 2, second order with respect to b, or it might be 0 order with respect to b, and that's essentially then it's just rate is equal to k a to the power of 1. What is it that causes this, and why should we be interested? Well, looking at rate equations can give us some insight into the mechanism by which the reaction occurs. And in order to illustrate this, we're going to look at these reactions here. So, right, if we look at this one, I have got bromoethane, and that's going to react with sodium hydroxide. Of course, it's only really the OH minus ion that reacts with it. It's a nucleophilic substitution, and you end up swapping the Br for the OH, and you get that. You get the alcohol. This reaction is extremely similar, except this time, this thing here, I've just drawn it to show you what it looks like. So it's a tertiary haloalkane. So the bromine is attached to this carbon, which is attached to 3 others, whereas this one we'd call a primary haloalkane because that bromine is attached to a carbon which is only attached to 1 other. Now, a tertiary haloalkane. And what happens is OH minus reacts with this one. You get a nucleophilic substitution. It swaps the Br for an OH, turns it into an alcohol. So superficially, they look very similar reactions. When we look at the rate equations, though, you'll see that they're fairly different. Okay, so if you look at the rate equation for this one, black one, you see that rate is equal to K. Now, rather than write out the haloalkane, I'll just write halo to the power of 1. And OH minus to the power of 1. So it's first order with respect to the haloalkane and the OH minus. So this is second order overall. Whereas this one, if you look at the rate equation for this, you do the experiments and find out. You find out that in this case, rate is equal to the concentration of the haloalkane to the power of 1, and 0 order with respect to OH minus. So it doesn't matter if you change the OH minus concentration, it has no effect on rate. Of course, we normally leave that off. So this one would be first order overall. Now, this is where we need to talk about something called the rate determining step. Write that down. So usually reactions occur in more than one step, might be several steps in the mechanism, and one of them will be a lot slower than the others. And we probably have one which is much slower, and this is the rate that determines the speed of the overall reaction, because it doesn't matter if you speed the fast parts up. What's slowing the whole thing down is how fast the slow thing's going, the rate determining step. And the classic analogy to this is if you've got an omelette factory and you've got chickens laying eggs and you've got a man frying the omelettes, well, it doesn't matter how good the man is at frying the omelettes, how fast he does that. What determines the rate of omelette production is the rate at which the hens are laying the eggs. Hopefully you get the idea there. Right, so let's see why you get, so we'll look at the this is the primary haloalkane. We know the mechanism for that. We've done it in organic chemistry. So what happens is CH3, I'll draw it like that. Okay, the OH minus, we've got a delta positive on this carbon with an electronegative bromine, and so that goes onto that, and simultaneously that breaks, and you form the alcohol. Now that happens in one step, and because there's only one step involved, that must be the rate determining step. And that's why if you look at the the equation, right, is first order with respect to both of them, haloalkane and OH minus. So let's think about collisions. If you double the concentration, it's first order with respect to both. If you double that, the concentration of that, the chances of these two things colliding is double. So the rate of reaction will double. If you double the concentration of OH minus, the chances of them colliding are doubled. So that will also do. So that's why it's first order with respect to both of those. And very often, you can tell what the rate determining step is because the two species in the rate determining step will appear in the rate equation. Let's have a look at the tertiary haloalkane. Now that actually occurs through a different mechanism, and it's probably quite revealing to say that if you just looked at the rates of these reactions, right, this one with the primary is a lot slower, maybe 10, 20 times slower than this one here. And so it's kind of evident if you just look at the overall speed that there's something different going on in those two reactions. Right, now what happens with the tertiary one is you've got your now if you remember, well, let's think about carbocations and the stability of carbocations. You probably remember tertiary carbocations are much more stable than primary carbocations. So what actually happens in this reaction is you don't need any OH minus. The Br will just drop off spontaneously by itself. It has a tendency to do that. And when it does, it'll be an equilibrium reaction. You form the tertiary carbocation. And don't forget that will be a lot more stable than the primary, because remember that the alkyl groups have a tendency to push electrons away from themselves. You remember that from we did about alkenes. Okay, so this is a bit more stable, so that's why it can form. Whereas with the primary haloalkane, you would have formed this carbocation. You'd only have one alkyl group. I draw it out like that. You'd only have one alkyl group pushing negative charge into there, so that positive would be more intense, and so that would be less stable. And that doesn't happen with the primary haloalkane. Anyway, so we form this, and then you've got some OH minus hanging around there, and that will very, very quickly react with that to form the alcohol. Okay, so we've got two steps in that reaction then, unlike the other one where there's one step. And OH there. Right, now this is the rate determining step, this one here. That is much, much slower than this one. This is very fast, okay? So as soon as you form the carbocation, it doesn't really matter how much OH minus you have hanging around. It reacts so quickly, it's way, way faster than this first step. This step is holding up, the supply of the carbocation is holding up the whole reaction. So how can you speed up the rate of formation of carbocation? Well, you could increase the concentration of the haloalkane. So that's why in that mechanism, you find it's independent. The rate is independent of the hydroxide ion concentration. It's zero order with respect to the hydroxide ion concentration. And it's first order with respect to the haloalkane. Okay, so that hopefully will give you some insight into rate determining step and how that can that will affect what the rate equation looks like. So working backwards by looking at the rate equation, we can make some suggestions as to what the reaction mechanism is.